We're Group 27 and we're doing a project about Mars orbital landing using reinforcement learning. My project mates are Venjun and Tamogna, and I am Ishan. So we'll be moving forward with the presentation. So introducing the outline of the project, we are going to go through the introduction, deep Q learning, policy gradient, actor critic, and the conclusion. So what motivated us to do this project was basically the SpaceX Falcon rocket retrieval. We also wanted to explore more reinforcement algorithms, and basically AI is the future, so we all wanted to get on board.
Produce an introduction to our new environment. Our new environment is based on the OpenAI Gym Lunar Lander V2 environment, but the original environment is very simple. As you can see from the picture, the rocket will always land in the middle of the terrain, and the terrain is very smooth. Our new environment, which is called Lunar Orbiter, and you can find this on OpenAI Gym website, and you can use this to train your own models. Our new environment has more mountains and slopes. There's a lot of spikies, and the flag is always random in the terrain, so it can be anywhere, and the rocket will have a great difficulty to find it. This is our project challenges. The first thing, as I have said, is the flag position. In the baseline environment, is always in the middle, and there is a wide platform. But in the new environment, the flag is random. It could be anywhere, and very big. It could be very close to the boundary. The terrain has more mountains and large slope, so it will be more difficult. The rocket ship also will make it more difficult because it have high gravity center and small leg angles, which makes it less stable. All the things we have done is try to make the task different and more difficult so that we have to improve our algorithms and dive into reinforced learning more. That's our goal.
Algorithm we implemented on the new environment was the DQN. So the following slides contain a lot of information about the Q-learning algorithm and all that, and all the subtleties of it. I'd skip this and go directly to the results to show you what we have actually got. So the training results that we actually got is been presented on this YouTube link. As you can see, it does pretty okay when it comes to really rocky edges, but quickly does better when it finds stable ground. As you can see, it's already doing better. The only problem that the we faced during training this was when the terrain is really rocky near the flag, it doesn't how it doesn't hover around and avoid the obstacle. It goes right on the peak. As you can see it right now, it's just going right on the peak and it's not able to maneuver around it. Now moving on, we can see the episodic convergence right here. This algorithm converges around 550 to 600 on average. On the left hand side, you can see the graph which shows the average reward per 100 episodes, and the other one is the reward per episode. So now I'll hand it over to Venjun, who's going to take over the policy gradient performance.
So why we need policy gradient is that Q-learning has some inherited shortcomings. So that and the policy gradient has some corresponding advantages. First of all, is better convergence properties, and the second, policy gradient can perform better in high-dimensional and continuous environment. And the third one is policy gradient can learn stochastic policies. Again, I will directly show my result. So this is the beginning of the training. As you may say, the rocket crashed for every time and it couldn't fly. This is the second video that has trained for 200 episodes, and gradually the rocket can learn how to fly, but it cannot land on a proper position near the flag. It will land like randomly on a place. Then this is the video after 500 episodes. You see, it will go to the flag directly and land properly. The successful rate is pretty high, and the training performance is very good. Yeah, that's it. I have some failure analysis here to analyze why it will fail, because our environment is very difficult. Sometimes there will be a high mountain, and in the state function there is no variable that can tell the rocket where is the mountain. So when there is a big mountain or big slopes, the rocket cannot land properly. That's the biggest failure reason. So this is my plot. After about 500 episodes, it can learn properly.
Algorithm we tried is actor critic algorithm. So the actor critic algorithm has two parts, actor and critic, and the following slides give an in-depth knowledge about the actor critic algorithm. I'll directly go towards the result for the model. The output plots are as such. The left-hand plot shows the rolling average, which is the previous 100 iterations, and the right-hand slot is the plot is the actual rewards got for each episode. The actor critic model actually performed pretty worse compared to the other two models. So the video is as follows. As you can see that I am running the code, and the training is pretty bad. It gives very bad results initially, and after a lot of training, it took around 3,500 episodes to train the model. It actually landed on near the flag. So the training is pretty bad, and it actually performed worse than the other two models. So finally, as a conclusion, on the three algorithms which we used, which are policy gradient, deep Q network, and A3C, we can see that the Q learning model took the least time to converge. It had around 550 episodes. The policy gradient took just 50 episodes more than that. The actor critic was the worst model. The average landing performance was the best for the policy gradient. It took for a case of around 50 testing episodes, it landed around 35 episodes time. So that was the best performing model for us on the new environment. Q learning was the second best, and actor critic was the worst. I thank you. That was our presentation.